I will just combine both things. Okay, so welcome again. Thank you very much for being here. As I promised you, today we are dealing with two species. Okay, and from the very beginning, let me start with a usual classification of interaction between two species that the ecologists and biologists use. Just to say, okay. Help, Jordi. I don't think it works. I don't know why. Okay, so this is a standard classification, mutualism, competition, and then you can for sure find or meet many of them in different examples in nature. So you have typical, so the honeybee and the flower, the clownfish and the sea anemone. So you have many cases of interaction between all of them. The symbols plus and minus and zero means if one of the species take advantage of this interaction, and zero means that it's totally neutral. Okay, so you have many of them. So let us go into mathematics inside this interaction. So there are examples in nature, and even all these kind of amensalisms and also neutralisms, which are not so common, but also they appear. Okay, I would like to start with a very general case. I go to a particular case which is really simple, but even in being simple, it's also interesting because it contains in particular the typical lockable terrain interactions and many of them. So let me do what is called Kolmogorov systems, which are just systems of a very particular and general form. So they are of the form x dot, and then you have something which is xy, and then functions which depend on all the variables. That's all. 1, 2, and n. They are called Kolmogorov systems. Usually, instead of working with them in this way, I will, many cases, just take this point, this xi, dividing here, and this is just referring as this is a relative growth of a species regarding its size, and this is something which depends on the rest of species. Okay. One thing which is very clear from this part is the following. So from here, you get that when a species is 0 at the very beginning, it remains 0 forever. So in other words, the coordinate planes are invariant. I mean, if you start in one of them, you remain there forever, which is quite normal. You know, this is very important because this means that they are barriers to dynamics. I mean, if you are in, you cannot exit from it. You can reach in, but always in infinite time. And then they can determine something which is an invariant domain. And for us, it will be very important. You will see at the end of the lecture today that if you deal with maps, this is not longer true. And then it means many other difficulties, okay? Well, this is very difficult and very general. So let me just do a kind of reduction. The reduction I'm going to do is the following. Okay, this F is very difficult. Let me start with something that we can deal with. So this means go into the linear case. And if you go into the linear case, I put this in this way, but this is an abuse of notation. I mean, if this xy is 0, means that everything is 0. They are this form, Ri, and something which is depending on the rest of the species. So this interaction depends in a linear way of the rest of the species. And if you are not comfortable with this way of writing it, let me put it in this way. So this is, you can put this and all the variables, assume they have any species. This is a kind of vector, which is, okay, I need more. May I just take the blackboard down, or you are still writing this? Sorry, or the letter is too big, or the blackboard is too small. So it's a problem with size. Okay, so just going this. The typical form I will deal with is in vector form. This is something which are constant. And then you have a matrix, which is A11, 2, and n. In fact, this is 0, A21, 0, A to n. And then you have n1 and 0 here. Apply to x1, x2, xn. So I'm going to just to reduce myself to this kind of systems. Okay. So let's try to translate into dynamics. What does it mean? This relative growth depends on something which is intrinsic growth, and something which is given by a matrix. This is an interaction matrix. Okay, so depending the characteristics of this interaction matrix, we can have competition, or we can have cooperation, or we can have both. For instance, if all the terms out from the diagonal are all negative, this is a competition system because they are competing. If, on the contrary, all the terms off from the diagonal are positive, this is a cooperative system. Okay, and you will see that, for instance, if you take matrices which are positive, matrix A, this is A, is positive of diagonal. I mean, out from the diagonal, all the terms are positive. They are usually referred as Menzel matrices, or if it is the contrary, they are called Z matrices, and they have very good properties regarding their eigenvalues, etc., etc., etc. And they appear in many, many cases. I just put here, in the case that is positive as Z matrix, all the terms positive as Z matrix. If all the terms are negative, it's called a Menzel matrix. And if you remember the first lecture of Mayra Aguiar, she was talking us about a method to compute the reproduction number RT. Okay, there is a very well-known method which is called next generation matrix. And the next generation matrix is based on this kind of matrices. They have very good properties, and you know which is the behavior of the eigenvalues, and you can find for the largest eigenvalue in this matrix just using that they are of this particular form. So observe, this is a kind of a algebraic way of seeing my systems. Okay, this is very particular, this is very simple, but it contains many, many cases. If you just restrict yourself to this particular kind of systems, these systems are called Lotka, Volterra systems. Even though the first original Lotka-Volterra system is a predator-prey system, which means I should be able to write a matrix, and some terms are positive and some other are negative. Okay, but in this way you can write cooperative, competitive, and also predator-prey systems in a close way. Okay, so this is my idea. I'm going to work with this. I want to analyze, as Jordi told us this morning, I'm going to do very simple mathematics. So I love to do very simple models, but even though I think they can be interesting to discuss. Okay, so forget about n dimensions. I'm going to reduce myself to n equal to 2, so 2 species. but you can do many, many things with higher dimensions. Okay? So let's continue with this part here. So a competition model. Well, typical competition model, the simplest one I want to work with is of this particular form. So you observe, I think I can do it just the screen. If not, I will need more time. Okay, the typical one is you get, this is a particular, I think from home, like they cannot see me. So equation number 5, they have a part which is the logistic model. So I think it's much better if I write on the blackboard. So my first competition model. It is based on what? Okay, you have two species. If there is no interaction, you can assume that they are just driven by a logistic model, and then they interact. And of course, the interaction must be negative. So you can write it in this form. So you can say this is 1 minus x1 k1, the current capacity. This is the same for the second species. Different current capacity. And then you allow them to compete. And when you allow them to compete, this is something like of this form, C1 and the product, minus C2 and the product. And then you are assuming that C1 and C2 are positive. This is the typical way you write or you model a competition between two species. Okay? Just let me write in this form, and you can recognize which is the interaction matrix. That is very, very simple. So observe that in this case, you can write it in the following form. So you divide, the same for x2. And what you get is something of the form R1, R2, plus your matrix that should be something like of this form. Tell me.
The diagonal elements of the matrix.
Yeah, R0, isn't it?
Aren't they minus 1 over k1?
Yeah, because you divide. So you divide by x1. You divide by x1. So you have, this is the constant part. Okay, sorry. And this is minus. So this is minus. You are totally right. I don't care really about this because in order to classify, it is not important. Yeah. So the terms which are out from the diagonal are negative. So we are competing. We already know it. Okay. So let me just deal with this model and which simple things I can do with it. Okay. So let me do some kind of a standard differential equations analysis with it. So first thing you know, we have that this x1 equal to 0 and x2 equal to 0 are invariant. So if you start here, this is x1, this is x2. If you start here, you remain here forever. And this is good for us. I mean, this is a good model in the sense that we don't want species to become negative. Okay? So let's continue. Something which is very important, I'm going to do, and is often done in ODEs, but has not a counterpart with maps, is let me introduce new variables in such a way that my system becomes the simplest possible. Of course, be careful. If you do this, you lose the intuition of each variable. But for us, mathematically, it's very correct and it's very accurate because you are losing variables or you are losing parameters. One typical one could be this here. So x1 over k1, you call u. In this way, you are just like saying you are normalizing to one the current capacity of the first species. You do the same for B. And also you can introduce, if you want, a kind of a change in the time, which is the first part here. You make a change in time. Of course, be careful. This is very good for mathematicians, but if you want to translate, you need your dictionary. And then once you do this, you have a system which is adimensional in the sense that, okay, mathematically is correct, is simpler, but it does not reflect the real dynamics, because if something is increasing, I have to translate with my dictionary in order to know what's happening. So this is the new system with change. In this case, you have 3 parameters, rho, A, and B. And then, which is a typical way you deal with these kind of systems? Well, you look for the skeleton. The skeleton is everything which is invariant. You could start with fixed points, equilibrium points, or you could start with something which is the null clines. Null clines are the solutions of derivative equal to 0. So this should be this case, for instance. So let me write in the blackboard, and I think it will be easy. So what's a null cline? Well, a null cline is in general a curve or manifold. So we have, this is my first equation. This is the second one. This is an A, I think, probably A. And this is y minus b with bu minus b. Okay, which is a null cline? A null cline is defined as the points, for instance, we have 2, such that u prime is equal to 0. This gives me the curve in the plane of those points where there is no change for a while in this variable. So crossing this curve, whatever it is, or the set of curves, where this variable u does not change. In my case, you have, or this is 0, or you have this line. And then you know that if this is a straight line, let me plot it in this way. You plot it in this way, and this is u prime equal to 0. This line in the plane divides the plane into pieces. One of them, this is positive. So for instance, I just plot in here, but it could be the contrary, just inventing. This means that u is increasing. Let me put in this way, which is more normal. So this means u is decreasing. And the contrary is here, positive, and this means u grows. If you do this for the 2 variables, you can have a more or less idea, grosso modo idea of the movement of your variables in the plane, okay? And sometimes it's enough in order to know what's going to be the omega limit or your orbits sometimes, okay? The good point corresponding null clines is that if you intersect null clines, what you get is equilibrium points. And this is very geometrical. So you have this, in my case, for the next first null cline, I have u equal to 0 or that straight line. In the case of B, I have B equal to 0. And the other one, and if you want, in a kind of generic case, you have many things just from this very geometrical information. So you have something like this. You have this. Remember, your null clines are this one, and also 2 lines. Just from this, you know that you have, this is shown that this is for u equal to 0. So v equal to 0, this one here. So this is a fixed point. And also you have the same for this. And then you have also this. So if you intersect these sets, what you get is an equilibrium point. And be careful, because in our case, each one of these has 2 pieces. This is u equal to 0, and the straight line, and this is v equal to 0 and the other straight line. So just combining this intersection, you know where the fixed points are. Okay, just plotting this, and then just using what does it mean null lines. If you are here, you know if you are growing, you're moving in this way, or in this way, or in this way. You have no idea about velocity. You have no idea about what the orbits do, but you know which is the tendency. Okay, so that's the first thing you can do. Second thing, you take the equilibrium points and you analyze locally, which is the thing that that Emma explained to us yesterday. So you just compute the possible equilibria. Observe, in our case, we have these 3 points because this is also an intersection of two null lines. And a possible coexistence point here. This is a coexistence point. And then you analyze locally. Be careful, everything depends on parameters. So depending on the value of the parameters, this point could be out of my system, my square, which is invariant, or not. So it has biological meaning or not. So that's mathematically typical. And then what you do is compute the Jacobian. For each point, compute the Jacobian, and then compute the eigenvalues. In dimension 2 is very easy. You go to dimension 3 or higher, this could be a really difficult problem because in very few cases you have a closed form for the eigenvalues, even though in the polynomial case. So typically it's quite complicated, but you can do it numerically. For instance, in this case, just pay attention on one point, the origin. You have 1 and rho are the eigenvalues. Rho is positive. So what does it mean that this is expanding? So the origin is going to be unstable, totally unstable. Depending on the value of rho, one line, one invariant curve or the other, because we know that this is invariant and this is invariant, is going to be faster or not. For instance, if rho is smaller than 1, this is smaller, it means that this second variable, so this is E1 and this is E2. E2 is the eigenvector related to rho. If this is a small one, means that the first one is the faster. So this goes faster in this way than in this way. So this means orbits will become of this form, tangent to the slope manifold. I mean, so you have an idea what's happening just close to this point. And you do the same for all the points. Okay, this is a typical way you do local information. Okay, just you can do the same, and you have all the computations here. Just I want to stress something which is interesting. For instance, in this case, you have that's the pen. In this case, you have eigenvalues. This is triangular, so eigenvalues is just the diagonal. You have -1, which is in this sense is attracting, and the other one, rho 1 minus b. Okay, depending on the value of b, this is okay, positive or negative, or is a kind of attractor or not. So it depends on it. What you get is for b equal to 1, observe that you have one eigenvalue which is equal to 0. So this means that you have a bifurcation there. So first thing you have to do is which kind of bifurcation I have. Second thing I suggest you to do, what's happening at the same time to the rest of points of your system. So does it mean some other point change stability, or some other point enters into the biologically meaningful domain? Because this is very interesting. Usually typical things is that they are really correlated. So this changes stability here, you have bifurcation, but then observe what's happening with the rest of points. And you could do the same for the other point. And of course, you have also the coexistence point, which is the real more interesting point, which is just what's happening in this point here in the middle. Okay. Tell me. Yeah. It's always, this is the slow variable. This is the fast one, and always x is tangent to the slow one, because this is, you're just doing more effort here than that. So you just increase faster in this sense than in the other one. So it's always tangent to the slow one. If it was equal, you will have something like this. Because when you just this is like having a tie. So you just take it from here, take it from here, at the same time, same strength. So this is a straight line. If you are just doing more strength in this sense, everything goes faster in this direction than the other one. So this is, and there is the stable manifold, unstable manifold that Ima told us the other day that they exit tangent to the local one, to the linear one, etc. So these orbits are like this. Of course, in this case, for me, it's not interesting because we are out from the biological meaningful domain. I'm only interested in positive U and B. Yes, Mark? No?
If the in one direction is faster,
yeah.
why do you think those are to
The faster is this one here.
Yeah.
Yeah.
Okay.
It's just a question of you go, okay, you say, you put here, and you say, okay, you have two cars, and say, okay, in 1 second where you are. If this is faster, in 1 second, you will be here. On the contrary, in 1 second will be here. So you're going faster in this sense than in the other one. So, tell me. This is quick. The one you gain out, the things here like this. You win more in this direction than in this one here. I didn't plot it this way. Not the first one. Ah, sorry. No, my idea was. Sorry. I know the confusion. I want to be more, yeah. Something like this, more exaggerated. So you just, if you want, you are leaving the origin tangent to this line here. And you have a kind of parabola-like orbits. So they are kind of parabola in this case. Okay. Well, but in this case, it's just a linear theory around an equilibrium point. Well, this is good, but it's just a linear approximation. You have to also to compute then the global one. Let me go. So you do the same with this coexistence point, whatever it is. And then the difficult part is just to combine all this local information, trying to figure out which is the global behavior. Let me just put this as an academic example. This is with figures, very nice figures. So if you do this, you compute the same, you compute the points, you compute the local stability, and what you get is this behavior here. So you have this point is an attractor. This is always a repair. So in this case, it's a repeller. This is an attractor, and this is a saddle point. And how can we interpret this result? In fact, what you have is this, okay? And then you can even do more things, because this saddle point has a separatrix separating, this is the names where the names come from, separating the behavior, the dynamics in two parts. In this case, we are in the plane. All the points here go to this part here. All the orbits starting in this part go to this one here. And how can you interpret it? Okay, if you are competing, you have two species competing for the same resources, and the number of resources are finite. There is a principle called Gause principle that says that only one of them can survive. So saying, okay, why delta variant in COVID is just dominating? Because okay, they are competing two strains. The one which is much power is going to eat everything. So it's only one surviving. And this is the struggle. This is the principle of Gause saying, okay, in cases of competition, in general, what's happening is this: only one of them survive. Mathematically, it's not always the same. Also, you can have examples of coexistence of them. Okay, but this is just analyzing this model. Okay. Let me go further because I'm just suffering not to be. I have still 50 minutes. No. Okay. If in some moment I have to skip some detail, don't worry, you have the slides, and the important thing is just the ideas. Let me continue with this case. Forget about competition. I'm going to the traditional lockable Terra systems, okay? Which is a standard one. Ima told us about this yesterday. So I'm going to, just to skip some points, I'm going to dilate some short results complementing this idea. Okay, you know, this history is, they just deduce the model in an independent way. The first one in principle seems to be Vito Volterra, just looking at the fishes in the Adriatic Sea where he was living. And they observed that there were two kinds of a prey and a predator. And if you just compute the time series, you observe a kind of oscillations. They were just in a kind of order way. So coinciding after a maximum of one of them, there was a minimum, the other one was just taking a maximum, and so on. And they just compute a kind of model in this way, or a similar one, where they try to represent what was happening in this case. All of you, for sure, you know this model. In my case, N is the population of prey, P is the predator, and observe what you have is to just put in this way. You have N point, P point. The intrinsic growth, you're assuming that the prey, if there is no predator, increase in an infinite way. In the case of predators, if there is no prey, they just decrease exponentially. So you have this. And then you want to have this part, which is just the B and P, and this is plus C and P, no? If you write it in the form lockable Terra systems, you divide by N upstairs, by P downstairs. So you have this, this part is out, and then you have this, and you have this. And if you want, this is A minus D plus, this is 0 minus B, C, 0, MP. So it's one of my models, okay? In this case, the system is not cooperative, it's not competitive because we have one positive and one negative, okay? So I want to deal with this problem. The first thing you do is, as before, you compute. Okay, observe that again, it's a lockable Terra system, is a Kolmogorov system. You have that the coordinate axes are invariant. So what this means is that this part is relevant from the dynamical point of view, from the biological point of view. If you start here, you remain here forever. And this for us is good, okay? So this is positive invariant. If you stay here, you remain here forever, okay? If you are here or here, you remain also forever in the axis. And then you compute the fixed points, okay? If you have any doubt of you're going very fast, or if you think I should go faster, please tell me. No, it's okay? Okay, so you compute the points. This is not the thing I'm more interested in. You compute the equilibrium points, you compute everything, and what you get is that you have only one point, which is equilibrium, which is this point here. The origin, okay, origin means there is nothing, there is no prey, there is no predator, there's nothing more stable than that, because it's like this. So the interesting case is this point here. And this point here is the coexistence one. So just let me put it here in the plane. So I have N, I have P, and they have a point here that is coordinates I always forget, which is D over C, A over B. This is an equilibrium point. And then what you do, you compute the differential in this point, you compute the eigenvalues, and you realize that the eigenvalues are complex, conjugate complex. So the differential in this point, you compute the spectrum, so the eigenvalues, they are just of the form plus minus, say, lambda I. What does it mean? That I can say that in the linear approach, this point is elliptic, but if you are taking into account the nonlinear case, we cannot decide. The real part is equal to 0, okay? So as we learn from Emma lecture, we could try to look for a Lyapunov function. Let me derive the Lyapunov function in a direct way, because one of the big problems with this is, okay, which kind of Lyapunov function do I have to choose? That's a big problem. So let me do it in this case, because this case is very particular and it's strangely easy to derive. And this is the case. So I have this is n a minus b p, and this is p in this way is cn minus d. And let me just to manipulate this expression in order to get my Lyapunov function. How you can do it? Okay, this is derivative of n in, let me check which is the expression I want to choose. Okay, don't look at here. This is my derivative. Okay, I put just 1 n I minus b p. This is equal to 1. I do the same for the second one. So I have 1 over p c n minus d derivative with respect to time. It is also equal to 1. So they are same. Okay. So if they are the same, you can just do the following. So you have this part. Let me just pass this term to this part and this term to the other one. So if you want, let me just be clear. I have this part. This is this part here, 1 over p cn minus d. And then let me combine in a smart way. Which is the smart way? This part goes to here, I have a p, and this part goes here. So I have cn minus d divided by n. You have this equal to, and this is a minus bp divided by p dp dt. I continue. I put everything on one side. And also I simplify. In which way? This is c minus d over n, and this is just a over p minus b. Okay? I put everything there, and I continue. I want to prove something that Emma proved for us yesterday, but I want to have a bit more information. So if I put this here, I have this part, AP minus B, dP dt, minus C minus dN, dN dt, equal to 0. Okay, it's the same. And observe here, A divided by P multiplied by differential of P divided by T is just derivative with respect to T of A logarithm of P. If I do this, this part gives me A over P multiplied by this. With respect to this part, this is just minus B P. And I do the same for this part here. This is minus Cn plus D logarithm of n. And this is 0 for any solution. So it's even more than a particular case of the Lyapunov function. This means that this function here is constant on any solution. This is called a first integral. Is a first integral. Okay, is the one particular case of the V that gave to us Emma the other day. So if I take V as this is a particular Lyapunov function, provided I prove that in my equilibrium point, this is positive, and outside is bigger. But I can do more things. Okay, this means that all the orbits in this way remain constant. If I start in one of these curves, there are solutions, I remain there forever. But you can do one more thing, which is, in this case, let me just go into, you can say, okay, I know everything here. This is the Lyapunov theorem that Emma told us. If you do this, let me again do the change of variables. So call small p to the logarithm of n, small q to the logarithm of p. And what you get is that your system is Hamiltonian, the form that Emma told us yesterday. And if it is Hamiltonian, what you get? In a Hamiltonian system, you cannot have never a limit cycle. You cannot have focus. So this point must be a center. And also what you can prove that is a global center, okay? So everything is foliated for this kind of orbits, closed orbits, okay? Because it's Hamiltonian. You cannot have focus in a Hamiltonian system. The Hamiltonian system measure is preserved. So you cannot have something which is just constraining measure or just expanding measure. Cannot exist focus in a Hamiltonian system, in the plane, okay? So I have this. One more thing, which I think is quite funny. Let me take one of these periodic orbits and assume that you know your period, okay? So assume that you have one of these periodic orbits. You know that it is foliated of periodic orbits. And this is my point, which is, I always forget, but it should be like C over D, D over C, A over B, maybe, this one here, and take one of these orbits. These are the oscillations you can see in the you do time series. So the increase and the decrease of the corresponding variables. Okay, this is N, and this is P. Assume that you know the period, and the period is equal to T. So one thing that you could do is to take this, the integral on the period of this variable, and also you could compute, which is this value for n. And since this is on a period, you can take and divide by t, which is essentially the mean value of this function. Okay, what is the mean value of this function here, or of this one here? The mean value of this is exactly d over c. And the mean value of this is exactly to the component corresponding to p. So for any periodic orbit in this system, and this is very, very, very easy to prove. This is called Volterra's principle. The only thing you need is just to take the differential equation and integrate using that it's t periodic, and you just do manipulation, and in half line you get the result. Okay. Okay, this is very nice. This is very academic, but it's not realistic. Why is not realistic? It's not realistic. Well, I'm skipping this part. This is corresponding to the LaSalle's principle. It's very related to the corollary that Emma gave to us yesterday. So let me skip it. It is very interesting in order to get omega limits of functions where they are close to Hamiltonians, for instance, you want. So just have a look of it. And let me go for this part. I think it's more interesting because if not, I will be short of time. Okay, this is, you have the material, so I think you can have a look. If you have any doubt, just write me, please. And why this model is not realistic? Well, for many things. First, if you just make changes in birth and date and death rates, nothing happened. It's the same. In this case, you have two species, prey and predator. There is never extinction, never. Okay, this could be, as Jordi told, maybe it's quite difficult one species to become extincted. But the worst thing is that it is really is not structurally stable. I mean, if I take my system, this one here, which is very, very nice. This system has a center here, foliated by infinite number of periodic orbits. If I add any perturbation, small perturbation, the one you prefer, any of them, this is going to be destroyed. For sure, with probability 1, that is going to become a focus, attracting or repelling, but it's going to be stable in the sense that if I just perturb a bit, this is going to disappear. So it's very nice, it's very academic. It was the beginning of very many things, but it's not really structurally stable in the sense that for us, it's not a good biological model. And it's more perturbation, even if you introduce some noise, this is not going to happen in this way, but it's going to disappear. So let me just work a bit more. Let me go in a more, say, realistic modulus mathematics, prey-predator model, okay? And then I have to talk about what are functional and numerical responses. So assume that you have a prey-predator model. You have your prey. In this case, H will be my prey. The predator will be P. And I want to do a very, very simple model. Let me start with my intentions, and then I will just discuss a bit how to do it. First thing, what about the prey? I'm going to assume that if there is no predator, it follows a kind of logistic model, which is quite the standard, okay? So you can assume that you have this intrinsic rate. You have also H, 1 minus H over K. This is the current capacity, okay? Let's go into the predator. If you go to the predator, what you could think is first attempt is similar to the prey case, but it's not really very realistic. Why? Because in some sense, it is normal to assume that the current capacity for the predator depends on the prey. And the simplest possibility is to assume that this current capacity is a constant, small k, depending on the density of the preys. Why not? You don't need to have always the current capacity to be constant. It can be, in general, will be a function. And then I have to incorporate here in this model, which is the action of the predator on the prey. So my target is, which could be a reasonable, easy way to model this action. Okay, so let's go on it. So what happens, and this is devoted to Holling in 1955, 59, sorry. And okay, if you have if you have an increase in the prey density, there are two effects on the predator. So you have, first, the number of predators increases. Okay, there are more. Second, the predation rate increases. And this is quite normal. If you go to a bakery and you love cakes, and you have just one cake, you eat, but you have plenty of cakes, for sure you are going to eat more than usual. So this happens with a predator. And this could be two kinds of responses, the functional response and the numerical response, okay? So I'm going to model, I'm going to forget for a while on this. I'm not going to move this parameter here. This should be the functional response, but I'm going to deal with the numerical response. I want to try to model this effect. In which way? This is okay, just looking or trying to understand which is the time invested by a predator in order to eat a prey. So you are a predator, and in which way you invest your time? In two things. You don't have TV, so you only are focused on eating prey. So your time is divided into parts. The time you spend searching for the prey, and the time you need to eat the prey. So the handling the prey, that means you chase it, you kill it, you peel it, you cook it, you eat it, and you digest it, and also the time you invest for searching. Okay, try to model this in a simple way. Of course, we are just doing models, okay? So let's start. My time T is divided in two parts, T search plus T handling. Don't forget that and try to figure out which is this part, the effect of the predator on the prey, okay? First thing, which is a HA? It's going to be the number of preys captured by a predator in the unit time. It's the thing I don't know, but I would like to know. Okay, so this is part of my target. First thing, something which is quite spectacular, you can expect it. The handling time must be proportional to the number of prey you get. So this is quite reasonable, this part here. Okay, it must be proportional. This TH is time spent by one predator. Okay, why not? I'm not just saying it is proportional. Why not? Okay, it's quite reasonable. Second thing, okay, we're capturing. So first, the capture is very interesting because you are a predator and you reach a point, and then you have your area. This is the zone where you are just arriving, and then you observe. Okay, you observe and you observe the number of prey they are. Each prey you find there, you eat it. So this is going to depend on this area. Also, it's going to depend on the density that you have of prey. So observe that this, you have an area, this area is called an area of discovery or the search area. So you have this. Okay, the time you need to search, you have to multiply by A, okay? And then also you have to multiply by the density. This is the number of prey you expect to find in this area. So this is per unit of area, of course, okay? So you have this, and then there is that after having this is the part giving rise to the number of prey you eat as a function of this parameter. This depends on this parameter. This is the area, this is the density of prey density, and this is the time you invest to searching. So you have this expression, and you can derive an expression for the time, the searching time, okay? Second thing, you just add. This time is the search time, which is this one here. Sorry, this is this one here. And also the one you get handling. And then you have an expression between T and this HA. But you are interested on HA. So you just simplify, you just from here, remove, and you get an expression for HA. Okay, but this is the number of attacked prey by one predator in one unit time. You have to multiply by all the predators because it's just per one. Depends on the density of your predators. Just one thing to observe. If you plot this function, observe there is a kind of saturation. What is normal? I mean, you are not always chasing, you are not always eating with the same emphasis. You saturate, okay? So you go here, just a comment. Regarding this behavior, Holling decided to suggest three main special cases of this evolution of HA in terms of H. And he called them type 1, type 2, and type 3. My case is type 2. So in many of these models, they say, assume that the action of the predator on the prey is Holling type 2. I'm referring that this is the behavior of HA regarding H. This is the density of the prey. This is the number of prey eaten by a predator in one unit time. Okay, so the second is my case. And then if you put this here. Just one comment. This case is very similar to the one that Jordi commented before. It's similar to Michaelis-Menten same model. Okay, this is not my case. It should be type 3. So if you put this is your functional response. We have to multiply. This depends on the time. So divide by the time and also multiply by the density of praise. And you have this expression for this action. So the model you get, this is the part, this part here is the one I'm going to include here. And when you do this, what you get is this model. This is a very well-known Rosenzweig MacArthur model, which is very loved by ecologists, okay? And it's very, very simple. And it's based on this kind. It's a kind of a Holling type 2 predator-prey model, okay? Well, this is very interesting. And you can play with it and you can discuss and you can go with it. But let me do something a bit different. Let me go into the discrete world. Okay. First thing, are really they interesting? Okay, yeah, they are very interesting. You can even extend this model and to incorporate a super predator. The super predator can eat the predator and even the prey. The predator eats the prey, and you have a 3 members trophic chain. Okay, X, Y, and 3. And you could even decide which interaction between, for instance, super predator and predator is by a Holling type 2. And between predator and prey is also Holling type 2. But you could decide which is the type of interaction you want. Okay, and we have enough dimensions in order to find interesting things. There are papers by Den and Heinz that if you assume that there are different time scales, so these predations are not at the same time, there are some difference. One is faster than the other. You can find chaos through a mechanism which is called Shilnikov type. So you find a kind of a connection, homoclinic connection of a particular type, okay? Well, this is not the thing I'm interested in. I would like to do something similar in the discrete case. So what about if I try to do the same with a discrete model? Okay, there are many works on discrete models. For instance, the very famous of Robert May about the logistic, but there are many, many of them. One, there should be the generalization of this predator-prey model, but in the discrete case, should be this low barrier model, which you can recognize that is, in a simple way, quite similar to a possible predator-prey, one in the ODE case. And you get, this is XY, you have this map, and you have this part which is mu 1 minus x over k minus mu xy, and then b xy, beta xy. Observe, this is the logistic, this is the competition, the interaction, so I'm eating, and this is essentially the dynamics for the predator. So I can assume that if there is no problem, he will increase, of course. If there are no preys, this goes to 0, and then the predators also disappear. And this is a map. This is a map. And similarly, you can do something similar for the super predator, predator, and prey case. So you could do something similar. Okay? 2-dimensional, 3-dimensional. Okay, can I do the same? Well, not really. Why not really? In the ODE case, remember that you have something similar like this. This is N A minus BP. From here, you get automatically that N equal to 0 is invariant. Is invariant. And the same for P. So what does it mean? That you start here, you never go out, which is quite good in our case. Well, in maps, this is not true. Even though you have here an X common factor in this part, or even here, a y, this does not imply that x equal to 0 or y equal to 0 is invariant. Okay, they are invariant, but you can cross it. That's the problem with maps. Maps are more difficult than in this sense than all these. You can cross it, and this is a Lai knows perfectly. It's plenty of discussions and no fighting, but discussions in the group. Okay, so you can just jump it, and this is a problem. Okay. Second thing, this is not bijective. This is not a Difeo anymore. So in this particular case, I'm going to refer to this case here. Given a point, you can have points with 0, with 1, and with 2 preimages. So everything is much more difficult. Okay, can I try to do the same? The mechanism or the technique we are used to is, okay, look for a skeleton. So we look for fixed points. And then what about the domain where this is defined? This is the first thing I'm going to do. And then try to figure out which is about the global dynamics. Okay, okay, there are examples of this, yes. When it's reasonable that I use a discrete model to work in the case of two species. If I'm really very interested in separating the offsprings, assume that we are just having data every one January the 1st. So this is something which is very discrete. So maybe I can use this kind of models, but of course be careful with the complexity because it can increase a lot. Okay, so take this, and the simplest we are going to define to consider is this triangle. Why this triangle? Well, at first sight, you can say this is in principle the triangle on dynamics has meaning. Why? Because you have here this term. If this term is negative, if you are out from this triangle, it has no sense. So I'm interested in positive x, positive y, and also here. This zone is x plus y less or equal to 1. If I have one xy which is not satisfying this point, it has no sense, because then on the first iteration, the next point is negative. So game over. Okay. I'm really interested in those points that when I apply t, they still remain positive and they have sense. And that's just the start of the story. What's the first thing you do? As I told you, you look for fixed points. Be careful, fixed points for a map is points which are invariant under when you apply t. So t of xy is equal to xy. And you can do it in a very easy way. And you find that there are essentially 3 kinds of points. One which is here, as usual, this is normal, this is the origin. One which is here. If there is no prey, you have just a kind of a logistic map. And then you have one here, which is coexistence. P1, P2, and P3. Okay? P1, P2, and P3. So this is the first thing. And you try to analyze its dependence on the parameters. In this case, we choose this particular rank of parameters because we knew that the dynamics is relevant enough and is interesting enough. Of course, if you increase the rank, there are much more, but even with this small part of the parameters space, the phenomena you find is huge, okay? And then what you do is you plot, which is the change in stability depending on several curves. And this is a bifurcation diagram for each point. This is for P2. You could have a asymptotic stable point, a tractor. This can be hyperbolic point, so unstable. This is unstable, but it's a node, a repeller. And this is the same for a hyperbolic. So you find many possibilities just to look for how depend on the parameters. That's very simple and it's very standard, I promise you. Okay, it's just a question of playing observe. This is only for the point P3. It appears in this parabola-like function on the right-hand side, and then have 1, 2, 3, 4 different types depending on where you are. So it's really very rich. But even more, something more freaky. What means more freaky? Means the following. Assume that you are here. Okay, you have a point, x0, y0. They're supposed to represent a density of prey and predators. And then you apply t. T of this point is equal to x1, y1. And the question is this point inside the triangle on everything is well defined? And you observe that not. If you are in these particular regions, red, you take a point here, when you apply t, you go out. So anytime you apply t, there's a region which is a parabola-like that you have to remove. Second thing, the rest of points, so everything in this triangle except this red part, when you apply t, where they go? To this triangle here. So if you go to this triangle here, game over. And then something that maybe for ecologists is not so interesting, but if you are a mathematician, you have a lot of curiosity and say, okay, which are the number of points that in 2 iterations I'm out, and in 3, and in 4. What's happening with them? And then you start playing, and this is the thing you get. For instance, if you want to ask you which are the points that when you perform all the iterations, you are always inside. You have this case for different values of beta and mu, or this case, or this case. So it's a huge variety. And then let me go to this. If I able to play the movie is built just the second part, and it was Bly who did it. Okay, there is a kind of a colors code. So the points in this triangle that in just one step go out, they are colored in black. Okay, then violet in 2 steps. And you decrease the intensity of the color depending on the number of steps you need in order to go out. And this is the points remaining in the end. So these are the points that do not escape. Observe this kind of fractal distribution. They are like fractals, this part. And we could say more things, but I'm not going to do it. Let me try to play the movie. And if I... He sortit? No. No? Canvio de pestanya. A veure. No? You think so or not? No. Okay, so no. Ah, sí, no, slide. Sí, és de nova slide. És un link.
Ah, però el que passa és que no s'ha obert. I no se t'està obrint la...
Okay, I know, yes. Okay, observe. It is creating step by step all this part. Okay, so I play it again. Okay, no, I don't know why it doesn't work. No. Okay, it's still doing, sorry. So you have the equilibrium points, and then you plot those points which are leaving the domain in 1, 2, 3, 4 steps. And then upstairs is just the remaining. Okay, the question was, and this was a source of a big discussion between members of the group. If you have one point or one orbit, then in a certain moment is out from this domain, can you consider it as a real solution, or you should consider that the variables are distinct? If you go out here, for instance, if you go to this part to the negative or here, can you assume that you are going to extinction of one of the species and then you restart, or mathematically you are assuming that it has no sense and this orbit has only a sense in a finite number of iterations, or even has no sense? So this is a big discussion. We were playing with this mathematically, but for us it was not so clear from the ecological point of view. This is a point of discussion. I will say that it has no sense, but this is something that we were discussing. Okay, let me continue with, no. Okay, I know. If I say no, this should be on top, really? Why on top? No. Means no. Okay. Why is not that? Oh, again here. Aquí, vale. Slate, sí. Sí. Sorry I apologize for that. I think that they are not people in they are not screen. Presentation. I find really ridiculous working with Windows. Can you see where is presentation? No. Okay. So open with Chrome. Oh, okay. No. I learned that is no.
Tomàs, si vas al vídeo, Tomàs, en el vídeo, apreta el comand de la pàgina. Aquí, vale.
Okay. Present. Oh, sorry for that. I find very ridiculous. Okay. I think I'm going to skip. There are 2 movies more. I think I'm going to skip them by obvious reasons. So this is part. Sorry for that. Okay, so you can, as I mentioned, you can do this, but you can do also more things. This is part here. There are some asymptotic results I'm going just to skip because they're not so interesting. But something which is really nice is to know, okay, I would like to compute in an easy way, which is the sensitivity of the orbits when I move in a transversal way. I mean, I take a point here. I take a point, put it x0, but this x0 means in R2, this is my point, but it does not mean x and y of my system. And then I compute the orbit. So this is x1, which is f of x0. This point is x2, which is f squared of x0, when f squared means f of f, not, etc. So I have my orbit. Okay, this could be continuous, and in this case is discrete. And then what I'm interested is in knowing opala, what happened with points which are close. So let me start here. So I choose delta naught, and I take this point. And I compute the images. The image could be like here. This could be essentially, they became in a very similar way. The distance is preserved. But I could, for instance, it could be like this. So it starts to separate and goes upstairs. So how can I measure in a simple way? In a simple way, there are many ways to do it, and there are more sophisticated, which is the value of expansion of contraction of the solutions close to a given orbit. Now this is called, one of them is called the Lyapunov, or the Constance Lyapunov method, which is, okay, take a point, choose a distance, and then you compute this here. So you compute the difference between this point and this point. You compare both iterates, okay? Fn means f composed with f n times, okay? Let me call this delta n. Okay, if I assume that this behavior is expanding, why not? So this is an assumption. If you think that this could be expansive or contractive, why not thinking that this delta n should behave like the first one, so the first separation, that is delta naught, and something which is of this form, so exponentially. If lambda is positive, the separation between them goes exponentially fast. If it is negative, it's contracting. And if it is 0, means that you more or less keep the same distance between these points, okay? And this gives you an idea if the solutions around a particular orbit contract, everything is contracting locally or expanding, okay? And how fast? If this was true, the element I will have to, or we like to compute is lambda, is the thing I don't know. How to derive lambda from here? Take logarithm, so you have delta n divided by delta 0. You take the logarithm, you divide by n. This should be this value for lambda. Okay, so I'm going to compute this numerically. I have delta n. This should be this, or you want